Welcome to Nerdy Dives. Today we are diving into DocETL, the paper that argues your LLM pipeline is wrong, not your prompt. 400 pages of police records. You ask a language model to find every officer implicated in misconduct. It comes back with 3 names. The real answer was 23. You didn't use the wrong model. You used the wrong pipeline architecture. Many of the major frameworks for LLM-powered data processing today were built around the same assumption. The user defines the operation, the LLM executes it, and the system's job is to reduce cost. Lotus, Palimpsest, Aaron, they treat your prompt as fixed, apply it to each document, return the result. That works when documents are short. When the text fits in one context window and the task is simple, extract the sentiment, summarize the paragraph. But LLM accuracy degrades measurably as document length increases. This has been shown empirically and characterized theoretically. The transformer architecture has well-known failure modes at long context lengths. Models pay selective attention. They focus on what's early and what's late. They miss what's buried in the middle. They hallucinate details that don't exist and omit details that do. And then there's the aggregation problem. You've extracted officer names across 200 documents, but each extraction ran independently. Officer Smith, J. Smith, Sergeant James Smith. 3 entries, 1 person. Your grouping step fails silently. You get 20 incomplete summaries instead of 1 complete one. No error. Just wrong output. A team at UC Berkeley, Columbia, and Berkeley's Institute for Data Science saw this pattern and named it. For complex documents and complex tasks, the problem is not that your prompt is wrong. It's that the operation itself needs to be decomposed, restructured into a sequence of simpler, more accurate steps. DocETL is their system, a declarative YAML interface for defining LLM-powered data pipelines paired with an agentic optimizer that automatically rewrites your pipeline into a better one. It uses LLM agents to do the rewriting, and a separate class of agents to evaluate whether the rewrite actually helped. The result is a new kind of query optimizer, not for cost, not for latency, but for accuracy. Before we get into the machinery, here is the payoff. On legal contracts, DocETL beat Lotus by 21% in F1 score. On biomedical drug reaction classification, it improved the recall-style precision metric by 80%. On police misconduct records, it produced officer summaries judged 1.34 times more accurate by both LLM judges and human reviewers. The rest of this video is about how a pipeline optimizer earns those gains without changing the underlying model. DocETL pipelines are YAML. You define a sequence of operations, each with a type, a Jinja 2 prompt template, and an output schema. The basic operators are familiar. Map transforms each document, reduce aggregates groups, filter removes irrelevant records, and equijoin connects records across datasets. But DocETL introduces 2 genuinely new operators. Resolve handles entity canonicalization. You write 2 prompts, one to determine whether 2 values refer to the same entity, one to generate the canonical form. DocETL builds the match graph, resolves each group, and propagates canonical values downstream. Embedding-based blocking, calibrated empirically for 95% recall, keeps pairwise comparisons tractable. This is the kind of operator that decides whether your final report is useful or garbage. When your reduce keys are LLM-generated strings, they will not be canonical. Resolve fixes that before it becomes your problem. Gather augments each chunk with peripheral context from neighboring chunks. Full previous chunks, summaries of earlier sections, just the fragments that anchor meaning. DocETL is not just chunking documents. It is trying to repair the context damage that chunking creates. The split operator divides long text into chunks by token count or delimiter. Straightforward. But splitting alone creates a new problem. A chunk in the middle of a police interrogation transcript may contain only pronouns. He denied it. She confirmed the timeline. Without knowing who he and she are, information that appeared pages earlier, the chunk is uninterpretable. And when you reduce across all chunks, you need the original order preserved, because some aggregations are not associative. Summarizing a textbook chapter requires reading Section 1 before Section 2. DocETL's folding approach handles this. Start with an empty accumulator. Feed in batches of documents sequentially. On each iteration, the LLM updates both the accumulated output and a scratchpad, a persistent working memory that carries state across batches. Instead of asking the model to remember everything at once, folding forces it to carry forward only the evolving answer and the notes it needs to continue. Optimal batch size is task-dependent and empirically determined. The optimizer tests multiple configurations on sample data. DocETL defines 13 rewrite directives in 3 categories. These are directives, not rules. An LLM agent interprets each one in context and synthesizes concrete operations for the specific task and data at hand. Category 1. Data decomposition. The primary directive rewrites a single map into a split gather MapReduce chain. Instead of sending the whole document to the LLM in one shot, you split into chunks, gather peripheral context for each chunk, run the map per chunk, and reduce the results. Smaller decomposition directives layer on top. Extract document-level metadata, contract parties, headers, effective date, before splitting, and attach it to every chunk. Run 2 independent maps on each chunk to extract the header lineage and generate chunk summaries, so Gather can render each chunk with full ancestral context. Filter irrelevant chunks after gathering. Skip the references section of a paper after you've used it as context. Unnest nested list results before the reduce. For reduce operations that aggregate large document groups, hierarchical decomposition. Aggregate at finer granularity first, then roll up. Reduce by city, then reduce by state. The intermediate pass captures nuance that a single, large-scale aggregation compresses away. These directives are abstract frameworks. The LLM agent decides whether any apply and synthesizes the concrete operations if so. The optimizer found that 47% of agent-generated plans outperformed the unoptimized baseline, which means roughly half didn't. That's why plan selection exists. Category 2 targets LLM-specific behaviors. The most elegant directive here is gleaning. An LLM that produces an incomplete first pass will often catch its own mistake if you show it the output and ask what it missed. Verification is often easier than generation. Gleaning formalizes this with 3 steps. The map runs first. Then a validator map, separate prompt, separate criteria, checks the output. Did this extract all officers? Are there instances in the document that weren't captured? If the validator says no, a refinement map takes over, receiving the original prompt, the first response, and the validator's feedback in the same chat history. The model sees its own prior output and the specific criticism. It doesn't start over. It builds on what it already produced. Repeat up to K times, or until the validator passes. The failure mode gleaning is designed to catch is not dramatic hallucination. It is quiet omission. Officer Y is not invented, just not mentioned. The validator, given task-specific criteria, reliably catches this class of error in ways that a single comprehensive prompt often does not. Gleaning doubles the LLM call cost for that operation. The paper consistently found it was worth it. The duplicate resolution directive handles entity canonicalization before aggregation. Before reducing by an LLM-generated key, run resolve first to unify semantic duplicates. In the declassified paranormal case file dataset, UFO sighting, category UFO sighting, and event type UFO sighting were 3 separate keys. The unoptimized pipeline extracted 233 distinct event types. Location aggregation per event type was meaningless. Most types contained a single article. With resolve, those 233 types consolidated to 83 actionable categories. Category 3 is projection synthesis. borrowed conceptually from push-down optimization. Complex maps decompose into chains, sequential simpler maps where each builds on the prior output. Independent subtasks split into parallel maps, then merged by a reduce. Before a reduce, project each document into a focused intermediate representation. Before an equijoin, preprocess both sides to shrink the comparison space. On the legal contract task, the optimizer chose isolated projection. 21 independent maps, each focused on a small cluster of related clause types, then a reduce to merge. The optimizer discovered that one giant prompt was worse than 21 focused ones. For targeted extraction, narrow prompts outperform comprehensive prompts, even across very long documents. That is often counterintuitive. More instructions in a single prompt does not always produce better coverage. The directives define the space of possible rewrites. The optimizer decides what to explore. In a traditional database, two correct query plans return the same answer. They differ only in cost and speed. With LLMs, two plans for the same operation can return different answers. That single fact breaks the classical optimizer playbook. You cannot minimize cost and assume correctness follows. DocETL's optimizer is a top-down traversal, inspired by the Cascades query optimizer from database systems. But the evaluation criterion is different. Instead of cost models, it uses evidence. Sample real data, measure actual output quality, compare alternatives empirically. For each operation, it first asks, is this already accurate enough? A validation agent synthesizes a task-specific evaluation prompt, not the user's prompt, but a separate check focused on accuracy, precision, and recall for this specific task. It runs on sampled data. If it passes, no rewrite. Move on. If it doesn't, apply matching directives. Each directive generates candidate plans. Newly created operations are immediately optimized recursively before the parent evaluation continues. Opportunistic decomposition. Only spend optimization effort on what's actually failing. Plan selection uses a two-stage process. Execute candidates on sampled data. Rate each on a 1 to 4 scale using the validation agent. Take the top 6. Then, pairwise comparisons between those 6. The plan with the most wins is integrated. The resulting pipeline is expressed entirely in natural language prompts, transparent, readable, and editable. Not a black box plan. A sequence of operations you can inspect and change. On the police misconduct dataset, the optimizer considered over 200 candidate variants and ran for 20 minutes. The evaluation covers 4 tasks. First, legal contract analysis on the Contract Understanding Atticus dataset. 510 contracts, expert annotated for 41 clause types. The task is span extraction. Find the exact text passage corresponding to each clause. DocETL's baseline is a single map listing all 41 clause types in one prompt. Lotus and Aaron implement the same prompt through their own systems. The optimizer chose isolated projection. 21 independent maps, each extracting 1 to 3 semantically related clause types, followed by a reduce to merge all extracted spans. The model does better when it's only looking for 2 things at once than when it's looking for 41. The focused prompts also avoid a well-known LLM failure mode. Comprehensive prompts on structured documents tend to produce outputs that are fluent but skewed toward the most prominent clauses, missing the obscure ones. Results on 50 contracts. F1 of 0.477 for the optimized plan. Lotus, 0.393, a 21.4% improvement. The unoptimized DocETL baseline, 0.379. Hallucination rate for the optimized plan, 0. For Lotus and Aaron, approximately 7%. The optimizer's own cost, $1.58, one time, does not scale with dataset size. The Biomedical Biodex task is the most striking result. The problem: given a paper, identify which adverse drug reactions from a 24,000-item MedDRA list are discussed. Lotus had reported sub-70% performance here. This was their hardest benchmark. DocETL optimized this into a map equijoin pipeline with synthesized blocking rules. An embedding similarity threshold of 0.5253, plus a hard requirement that all words in the reaction label appear in the article text. That second rule, simple substring logic, proved decisive. Reactions that appear explicitly in the text but have low embedding similarity to their MedDRA label were being systematically missed by purely vector-based approaches. DocETL's blocking synthesis surfaced them. Result at RP at 25, which effectively measures recall since most articles have fewer than 25 relevant labels. 0.371 for DocETL versus 0.206 for Lotus. An 80% improvement. At RP at 5 and RP at 10, 33% and 50% better respectively. On Steam game reviews, temporal analysis of documents exceeding context windows, the optimizer added gleaning specifically to catch temporal ordering errors. Hallucination rate dropped 33 percentage points, from 46.5% to 31.2%. Kendall's tau on chronological ordering improved from 0.47 to 0.63. On the paranormal declassified files, with resolve plus batched folding, the fully optimized pipeline extracted 435 locations at 100% precision. The unoptimized baseline extracted 233 unresolvable event-type duplicates with no meaningful aggregation possible. The police misconduct case study is where the stakes become concrete. 227 documents from California police departments, 12,500 average tokens per document, 2% exceeding the 128,000 token context window entirely. Multiple name variants for the same officer across hundreds of records. Unknown total case count. The task: generate detailed misconduct summaries per officer. Real names, specific incident dates and locations. Full descriptions, not generic labels. The naive pipeline extracts officer names per document, unnests to one document per name, and reduces per name. But the names were generated by an LLM. J. Smith and Sergeant James Smith are separate reduce keys. You get 20 incomplete summaries instead of one complete one. No error is raised. The output just quietly misrepresents the data. DocETL's optimized pipeline, selected from over 200 candidates evaluated in 20 minutes, adds metadata extraction before splitting, header lineage and chunk summaries through the gather chain, gleaning on each per chunk extraction, a within-document reduce before cross-document aggregation, and a synthesized resolve with embedding blocking. Optimization cost: approximately $100 on a sample of the dataset. That sounds significant, until you learn the Police Records Access Project has already spent over $50,000 processing this corpus. The $100 optimizer is a rounding error. The resulting pipeline was 1.34 times more accurate on all three quality criteria, with 96% agreement between the LLM judge and human reviewers. Here's the framing that makes DocETL's contribution precise. Traditional query optimizers rest on three assumptions. Operator correctness is guaranteed regardless of physical implementation. A hash join and a nested loop join return the same result. Subplans are independent. You can optimize in isolation, use dynamic programming, compose the best subplans. And cost is what you're minimizing. DocETL operates in a regime where none of these hold. Physical parameters, fold batch size, chunk size, gather configuration, change the accuracy of the output, not just its speed. Different fold batch sizes produce genuinely different outputs. Chunks cannot always be processed independently. Losing context changes results. And subplan accuracy is not independent. The best strategy for Step 4 depends on what Step 3 produced. So DocETL replaces cost-based search with evidence-based search. Sample real data. Synthesize task-specific evaluation criteria. Measure actual output quality on actual documents. Compare alternatives empirically. This is query optimization for when the executor is a language model. The answer to which plan is best is not derivable from a cost model. You have to measure it. DocETL is open source at docetl.org. 16,000 lines of Python, 2,000 lines of Rust for blocking and resolution. The broader lesson: as LLM systems get more complex, prompts matter less than the pipelines around them. $1.58 to optimize a legal pipeline. $100 to optimize a public safety investigation worth $50,000. Thanks for watching Nerdy Dives. If you enjoyed this deep dive, consider subscribing. It genuinely helps. See you in the next one.